going to talk about sort of a kind of a few lines of work that my group and I have been thinking about for the past couple of years, sort of centered around, as you can see from the title, optimality in optimization. And I should start by saying this is joint work with several of my students, Hilal, Yair, Ali Hinder, and Feng Ruan, and then my colleague Aaron is a professor at Stanford as well. But so these guys, all five of these have been sort of really central to everything here, and none of this would have happened without them. So they deserve a huge amount of credit. So in any case, okay, jumping in. So I guess the main problem in the talk that I want to talk about today is to minimize a function f of x subject to some constraints on x that it belongs to some kind of set capital X. Okay, that's the problem for today. And sort of the rough question, broadly that I want us that'll sort of illuminate this talk is, what does it mean to have an optimal method for this problem, or for problems like this? How do we talk about optimality? And so what that means is kind of, I'm going to sort of try to address this in three-ish parts, but some kind of sub questions that pop up in this are, what methods actually are optimal? Like, how do you define, how do you decide that a method is optimal? If we prove theoretical bounds, do these actually make a difference? How, just because we've proved that a method is optimal, does that actually matter for anything? And sort of a side question of that is, can we make theoretical bounds that actually make a difference? And then once we've got these, both empirically and in theory, how do we decide that a method works? So there's going to be kind of both theoretical and some empirical components to this talk. So let me begin by establishing some theoretical results and giving kind of a theoretical framework and sort of an overview of some great work that other folks have done. So sort of within optimization and statistics, I would say that the standard way of defining optimality is via Minimax or Minimax complexity. And this sort of comes out of what you might call the information-based complexity. And a lot of that work was sort of the early 80s with Nemirovsky and Yunin and Traub and Wozniakowski and some other folks like that. And so the ingredients are basically three parts. First, there's a class of functions that we want to minimize. These are functions mapping R into R. There's what we'll call an information oracle, and I'll usually use a sans serif O to represent this oracle. That takes in a point X, because we're doing optimization, and then returns some kind of information about F. Maybe this is function values, gradients, stochastic samples of F, things like that. And then we have a method, which is an optimization algorithm in this case, which then returns a point xk after sort of k queries to this oracle O. So there's sort of the three pieces that we're going to have. And our performance measure is to measure performance uniformly, which is to say by the worst function in our class. So if we have our method, which returns our point xk, we say its sort of figure of merit or its performance is measured in a uniform sense. It's sort of the worst of all the functions in the class. So if we say you do well, you have to do well simultaneously for everyone in every function in the class. Okay, and then this would be the sort of minimax optimality gap. And then the minimax rate, of course, is if we look over all possible algorithms. Here's an infimum over all algorithms. We look for the worst performing function in our class, and we look at this sort of, say, optimality gap or something like that. All right, so that's sort of the standard notion of optimality. Now, one funny thing about this is that it is sort of a gross notion of optimality, because you could certainly imagine a scenario. So let's suppose we somehow indexed all functions on this horizontal axis, and on the vertical axis we wrote sort of time to epsilon accuracy of our minimizers. Okay, and you can imagine, and I'll do different methods in different colors. So you can imagine that one method, is sort of it's kind of up here all the time. So there's method one, and for every function it sort of runs in the same amount of time, method one. Then you could have method two, which say is really good for most functions, and then once there's like one or two functions where it's not so good, right? Method two. And the thing is, minimax complexity would say, hey, this point right here, that is the, or at least that's the worst case complexity of method 2. And so in a sense that this minimax complexity measure already says that method 2 is worse than method 1, which seems a little weird since on most functions it's doing a lot better. It's just 1 or 2 it's slower. Anyway, I mean, already there's some issues with this, but I just want to highlight that to say, you should probably question a bunch of the approaches that we'll take at first, but it's because there are issues here. But we're still going to start with this minimax notion and try to understand things, and then maybe we'll be able to go beyond it a little bit or attempt to go beyond it in different ways. Okay, so super biased survey on minimax complexity and optimization. Probably the standard text is Nemirovsky and Yudin, problem complexity and method efficiency and optimization, and that's early 80s. This is a pretty hard slog, but it really has this sort of wealth of results and really got the field, kind of put the legs into the field. And more recently, there's been sort of a big growth and a lot of work, kind of starting in the early 2010s with Max Jaginski, Sasha Rockman, Alec Agarwal, Peter Bartlett, Pradeep Ravi Kumar, and Martin Wainwright, looking at sort of optimality and stochastic optimization cases. And more recently, Blake Woodworth, Nadi Srebro, and my collaborators and I have started to try to go back and revisit some of the ideas in Nemirovsky and Yudin, make them a little bit, say, easier to understand, and then extend them in different ways. So there's been a whole lot of work in this direction. And all of these papers here, all of this work are what you might call, we're working on what you might call algorithm independent bounds, meaning they're going to apply for any algorithm, randomized, non-randomized, whatever you want. So we'll make no restrictions on our algorithmic classes. There's been, of course, a lot of other work in these notions of optimality. Steve Ovasis has done some really great stuff. Coralia Cardis, what's Gold's first name? I'm blanking. Philippe Twant, Jar, Jim Reniger. These folks have all done really great stuff, often in sort of slightly more restricted algorithmic classes, but that often makes more of a difference in practice because it helps you understand particular algorithms. So there's been, suffice it to say, there's a lot of interest in this area, and there's been a lot of great work by other people. But let me now talk about kind of, just to give some sense of how one proves such bounds and investigates them and understands them, let me kind of try to give a few pictures of what's happening here. And along the way of giving these pictures, I'll be able to describe some of the results that we've developed. So what is oracle complexity within, say, convex optimization? We'll start with this case because it's kind of cleaner. You can say everything. It's very clear what you're proving. So we have an algorithm A. It's going to access this function f that we want to minimize through our oracle O. So A is sitting here. It sends a vector x into the oracle. The oracle says, okay, I got x. I compute some information, some oracle stuff, and I return it to the algorithm. And I go back and forth and back and forth. So you might consider first order algorithms. And these would do things like release a function value and a gradient. And a gradient. Oopsie, I can't spell, but it doesn't really matter. And a gradient, grad f of x. You might do what are called local algorithms or local oracles. And essentially what a local oracle is it's something that gives you back basically all of the derivatives of your function, or sort of information roughly equivalent to that. There's a more precise definition based on sort of open sets and neighborhoods, but I prefer to just think of it like if I had a C infinity function f, I would literally give you all the derivatives of my function f at that point, like infinitely many of them. Okay. And then the worst case complexity, which is this minimax notion we're thinking about, is the infimum over all algorithms in our collection of possible algorithms. And then we look at the worst function, as always. We just ask how many queries does it take A to find a point X with a small optimality gap. So this is our optimality gap is small. And then we're sort of interested in the scaling of the complexity, this complexity measure here with epsilon. So how fast does this go to 0 or I guess grow as epsilon gets small? So how many iterations is it going to take as we have to get more and more accuracy there? All right, so the sort of, there are some results that many of you may be familiar with if you've spent a lot of time in optimization. So when f is convex, we have pretty solid knowledge of this. So if we're just sort of thinking of arbitrary convex functions, then roughly, if I want epsilon accuracy, d times log 1 on epsilon function and value and subgradient evaluations are optimal. Okay, that's kind of the minimax complexity if we're allowed to use the dimension. And this is sort of intuitive. You can think in one dimension, just to say a binary search. You know, if I have a function defined on the interval 0, 1, I start off, say, at a half, and I ask, is the gradient positive or negative? And so I learn that the gradient is negative. No, that's positive. The gradient is positive. Then I know that my solution has to be on this side of a half. Okay, then I query another point, and I learn my gradient is, say, negative. Then I know my solution has to be on this side. And you can imagine we can just repeat this, do sort of a binary search, and it's going to take exactly log 1 on epsilon steps to get to within, sorry about that, log base 2, 1 on epsilon steps to get within some epsilon accuracy of a solution. Okay, so sort of this idea is clear, and in higher dimensions, there's sort of an analog, except with centers of gravity instead of a binary search. There are other more there are other different bounds. If my function f has a Lipschitz gradient, meaning that grad f of x minus grad f of y is less than or equal to L times x minus y, and let's say these are two norms, doesn't really matter, then roughly the square root of the Lipschitz constant times the diameter of x divided by epsilon, function value and gradient evaluations are optimal. And this is sort of both due to Nesterov, Nemirovsky, and Uden. So all three of them. The lower bound was Nemirovsky and Uden. The upper bound is Nesterov's famous accelerated gradient methods. If you have strong convexity, meaning your function grows at least quadratically, and you have this Lipschitz gradient condition, then you get sort of linear convergence mitigated by this condition number type penalty. Okay, so these are all sort of classical results, and if you've spent a lot of time in optimization, they should be fairly familiar. And if you haven't, that's fine. I mean, just these are, there's this sort of beautiful theory of developing these. All right, so, yes, sir.
Interactivity for you.
I love it.
Good to see you, by the way. So,
thank you, you too.
The third line, the L Lipschitz gradient, is because now you wanted a dimension-free lower bound, or because
yeah, if we want to,
you know, because this is worse than d log of 1 over epsilon, right? So.
Right. Yes, that's a good point. So of course, 1 on square root epsilon is typically much larger than log 1 on epsilon. But if I have a dimension in the front, then we have this question of whether square root L times this diameter constant is less than or greater than this d times log 1 on epsilon. It turns out there's actually, that Nemirovsky and Uden were actually able to give a sharp transition between these two. So as soon as you get to a dimension that's sort of larger roughly than this, then you're in this convergence regime, and this is the lower bound. And as soon as you're in low enough dimension where this is smaller, then this is achievable. So these kind of, there is a, I guess, a smooth transition between these. It depends on your dimension. It's a great question.
Cool, thank
you. Mm-hmm. And similarly, I guess there's a smooth transition between this and these. Just with sort of different dimension-dependent constants. Okay, so now the most common quote I read in machine learning papers on optimization, and it's possible that I've written this, and if somebody finds it in one of my papers, I'm sorry, but you know, this method is optimal because it achieves the minimax worst case lower bound. I read this all the time. This is an optimal method. And frankly, I find it a bit silly because, I don't know, it is silly. Because let's think about how we actually prove these lower bounds. All right, so I'm going to change the game a little bit. So now I'm going to actually present new results, or at least results that I was part of developing. And we'll look for in the non-convex case. So now instead of an optimality gap, the only difference, it's the same Oracle complexity model. I'm going to look for nearly stationary points. Okay, so I just want to find a point x. I want to find a point x that is nearly stationary. Nearly stationary. So because we know as soon as we're non-convex, we're never going to find a global optimum, let's just look for stationary points. And in some cases, this is going to be good enough for optimality, but in general, it's just, you know, it's a thing we can prove theorems about, so let's do it. Okay, so let's talk about how we prove, Tim, yeah?
Yeah, sorry, there's a question in the chat, and as in the Lipschitz case, if we have no existence or uniqueness, what do we do? I guess uniqueness is not a big problem, but existence, I guess, is assumed, or?
Oh, for this case right here, or this case?
Yeah, I mean.
So, yeah, this is a good question. If we, in this last case, when we have strong convexity, then uniqueness is there exists a solution and it's guaranteed to exist. I mean, there exists a solution and it's guaranteed to be unique because our functions themselves are actually quadratic looking and coercive, so there has to be a minimizer. In this case, this L-Lipschitz gradient, as soon as the space X is closed and compact, or is compact and convex, still a solution is guaranteed to exist because the functions themselves are continuous. So we sort of don't, in convex land at least, we don't worry about these kinds of things so much, you know. Sorry, I don't seem to see the chat, so if you have a question, feel free to just like unmute yourself and shout. It'll be easier.
No, okay. I'll be monitoring the chat.
Oh, okay, you're gonna monitor. That's perfect too. That also works.
Yeah, don't worry about that.
Okay, good. Okay, so this is what we're gonna kind of ask ourselves now. And as sort of a typical example here, the kinds of function classes we're going to be considering are based on different regularity measures, which is to say essentially smoothness measures on our gradients. Basically, we're going to assume that our derivatives of our functions up to some order p are Lipschitz. And then we're going to assume that there's some kind of initial optimality gap. We start off, we're within delta, at least in function value of optimum. And so if, for example, you have this delta gap and your gradients are Lipschitz in the non-convex case, well, then you could just run gradient descent, and basically 1 on epsilon squared iterations will get you a stationary point. Okay, but, and there are all sorts of variants of this. Okay, I'm going to skip this slide. I may come back to this in a little bit. Let me describe how we prove sort of optimality results in lower bounds in these minimax cases. So what's the anatomy of a lower bound? So basically there's this kind of two-part strategy. Part one is we sort of consider some class of nice algorithms, say represented by this little friendly robot fellow, and then we have bad functions, okay? So we got nice algorithms and bad functions, and this is what we'll use to prove lower bounds. And what a nice algorithm is, and I should say, as far as I know, sort of the core of this idea is due to Nesterov in his book, Introductory Lectures on Convex Optimization. The nice algorithm basically means that my iterates belong to the span of the gradients I've observed. Okay, and this is fine. I mean, think about gradient descent as one example. Certainly gradient descent will satisfy this because you always iterate xt gets xt minus 1 minus some step size alpha, say t minus 1, times the gradient of f at x t minus 1. So certainly gradient descent, you know, this always belongs to this span. And there are there are actually generalizations of this span condition to higher order derivatives, but generalizations to sort of pth order derivatives. But they're basically just notational hazards, essentially. Nothing actually intellectually sophisticated here. Just sort of notational hazards when we want to extend this to higher order derivatives. Okay, and so then there's a bad function. What's a bad function? So a bad function, well, in a convex case, is basically what you might call a quadratic on a chain. It's basically just x transpose ax, where a is equal to 1, minus 1, and then 2 is all the way down, and then a 1, minus 1, minus 1, minus 1, and then minus 1's all the way down. So basically you're just looking at a series of quadratic differencing operators. Okay, and why is this bad? Well, this is bad because it has this sort of chain structure where you get information about x1, but then x1 only somehow, I guess, you know, for lack of a better word, communicates or interacts with x2, and so on and so forth. So what's going on here? Well, let's think about the iterations of our algorithm. So we start off, and what I'm drawing here, I indexes my coordinates. So this is coordinate 1 of my vector, coordinate 2 of my vector, coordinate 3 of my vector, all the way up to coordinate d for the dimension. And then I have my vector, I have my vector x. So at iteration 1, I start off at the all zeros vector. Okay, so then what we're going to ask is, what about the coordinates of my gradient? What do those look like? well, for this bad function, the gradient is, of course, this difference of neighboring terms. And the only one that's non-zero at time 1 is the first coordinate. Okay, so as long as my algorithm is behaving nicely, the only thing that could possibly be non-zero at the next iteration is coordinate 1, because this is the only non-zero gradient entry. All right, we go 1 iteration into the future. All right, so then coordinate 2 maybe is allowed to be non-zero because now, you know, the first coordinate of x is non-zero. So right here, sorry, if I equals 2, we have negative x1. This might be non-zero for the second coordinate, but otherwise everybody else has to remain 0. Time 3, the same thing occurs. We're allowed to take 1 step down our chain. But so the point is that we're only going to get to go 1 step down the chain at every iteration of this procedure, right? And so essentially the number of steps we have to take is whatever the dimensionality of the problem is until we solve it to some appropriate accuracy. So this is what bad functions look like, is basically they have this kind of chain type structure. That means we just have to walk down 1, 2, 3, 4, all the way up to the dimension. Okay.
Hey, can I, it's Adam here. Can I pipe up with a quick comment?
For sure.
Also, especially since this is an applied math seminar, this example from Nesterov, I guess, is related to the discretization of the 1D Laplace operator.
Yeah, it's exactly the graph Laplacian.
Yeah. And I guess you can come up with other examples just coming from understanding this discrete operator and the fact that its condition number gets really bad.
Yeah, it is quite, so this is a very poorly conditioned problem. There is a way to make the problem well conditioned. Basically, I can add essentially a sort of regularization term, x2 norm squared, if I want this to have a given condition number. Rather than, I mean, exactly as you said, this essentially has a condition number, which is, what is it? Is it linear or quadratic in the dimension? I actually forget.
I think it's 1 over, well, d squared, something like that. I think that the eigenvectors are discretizations of like sine.
Yeah. So it's going to be quadratic in the dimension. So yes. So the condition number of this guy is basically, oopsie, of this guy is basically dimension squared.
Yeah.
Yeah. Thank you. Yeah. So it's really terrible. We can fix that a little bit by, oopsie, that was not what I meant to do. I apologize. So we can fix that a little bit by adding some kind of quadratic regularization to deal with sort of, if we want to have these things for well-conditioned problems. So there are sort of sophisticated things, more sophisticated versions of this that we could do. But yeah, as a side note, like this dimension dependence, you really have to have it be dimension dependent. And so we have to have algorithms that essentially will work for all dimensions of problems.
And John?
Yeah.
What about the Adagrad algorithm from a famous Californian?
Yeah, what about it?
Well, it's not nice according to your definition, so.
Yeah, so that's a good question. So what if algorithms are not nice? Like what if they don't obey this sort of span type condition or things like that? So here's the answer to that. It's okay. Let me give you 2 answers to that. We don't actually require this. We just require that the zeros of xt are a superset of the zeros of the gradients of f of x I. Okay, so as long as the gradients of as long as the coordinate gradients remain 0, that's all I care about, is that these are 0 or non-zero. So we don't really care about the span exactly, we care more about the 0 structure. So we just make sure you get literally 0 information. It's like, nope, you're 0 at the end. So Adagrad does actually kind of fall into this, but I can give a slightly more sophisticated answer to this, which is the following. Okay, we can actually show that the complexity for, gosh, keep pushing buttons, these sort of 0 respecting algorithms, meaning things that whose zeros stay 0 if you get nothing about them, no information, their complexity is actually better, or at least as good as all deterministic algorithms, as long as your function class is sort of rotationally invariant, meaning that if f is in f, then the function x maps to f ux is also in f for all orthogonal u. Okay, so if you can rotate, and most function classes sort of satisfy some kind of thing like that. Basically, if I can change my coordinate system, any deterministic algorithm, I can essentially force it to behave as though it respects zeros, because my sort of I can have some kind of adversarial oracle who constantly is rotating space to force u to be zero. Anyway, but so I can do this. And then for randomized algorithms, actually the same idea goes through. Basically, what I do is I just replace I replace f with f of ux, where u is a random rotation. And so if I take this sort of hard construction and I randomly rotate it, it turns out that almost, I'm not being 100% accurate, but I'm almost being 100% accurate. Basically, I just randomly rotate these sort of worst case functions, and then no algorithm can do well. And so I just pick a random coordinate system, and essentially you can't get any useful information.
Thanks so much. That is so cool. I always wonder about these things. So thanks.
Yeah. So this random coordinate system, actually, so Blake, Woodworth, and Nadi Cerebro kind of came up with the construction, and then Yair and Ali Hinder and Aaron Sidford and I, well, there were some technical mistakes in this, but it's fine. They had this beautiful idea. It's just hard. The probabilities are hard, and we kind of cleaned it up and then sort of figured out how to apply it beyond convexity as well. But yeah, so now what happens when we try to go beyond convexity? Because we also have lower bounds for non-convex optimization. And here, you go into the realm of, I'm sorry, this is a dad joke, but I'm a father now, I'm allowed to tell these. You go into the realm of science fictions, you have psi and phi. So you have the sci-fi function. Yes, I got one thumbs up. But the point is that, yeah, since we're allowed to do non-convexity, we still have this same sort of chain type structure. But now our functions are a little bit more perverse. So this function phi or phi is actually the Gaussian CDF. It's just the probability that z is less than or equal to t, where this is the Gaussian. And then psi is this weird C infinity kind of bump function. Like this function, if you've taken sort of functional analysis, you've seen this when you want to do weird like partitions of unity and stuff, or compactly supported C infinity functions. But the point is, it's just this perverse function, and you stick it in here, right? So that you basically have this kind of chain structure where you're still going to be forced to walk down x1, gives you information about x2, gives you information about x3, gives you information about x4, etc. No matter what, you just have to walk down the chain before you can actually solve or even get to stationary points of these problems. So anyway, so the point is that now, actually, we realize the minimax lower bounds for essentially all finding stationary points of sort of non-convex problems. And I can tell you exactly what those stationary points are by going back several slides and just telling you going here. So what are the minimax rates here? Well, we have upper bounds of, say, 1 on epsilon squared to get to an epsilon stationary point for gradient descent. So recall that what we're trying to do is get to a point where grad f of x, oh, I can't really see that. Here, we'll do it in blue. Recall that we're trying to get to a point where grad f of x is less or equal to epsilon. So gradient descent does this in epsilon minus 2 time. Newton's method can do this in epsilon to the minus 3/2 time. And then there are sort of interpolations between these using sophisticated line search and backtracking strategies that we've been able to develop. But the point is that actually now we have proved that these are all sharp. So this is sharp, and you can actually do this for all orders of algorithms. And so in general, if you have sort of pth order smooth derivatives, then you're going to get epsilon to the minus p plus 1 divided by p is the sort of optimal complexity for these. Okay, and actually we can show some sharpness in a related setting, but I'm not going to worry about that for right now. Okay, so we have now realized our minimax lower bounds. There's this minor issue, which is that this doesn't actually look like a function that I would ever want to optimize in my life. It's sort of a fun theoretical construction, but it has, I mean, frankly, like, this doesn't look like anything I would ever solve. And so we've proved that certain methods are optimal, but then we went and just decided to run some simulations, okay? And I'm going to now solve a nonlinear regression problem, a robust regression, with this loss function, phi of t, which is t squared over 1 plus t squared. So it's sort of shaped like this. Now, it's a smooth function. It's the kind of thing you see in robust statistics. I want to minimize this robust regression problem right here with this loss. All right, and so we ran 5 different methods. There's gradient descent, which is supposed to be sort of optimal among Lipschitz continuous functions with Lipschitz derivatives, which this is one of them. We ran our fancy algorithms with sort of randomized restarts and things like this. That's algorithm 3 with some exploitations, restarting accelerated gradient. And then, we went and downloaded some code that folks had written in, 1970 when they were real engineers on using nonlinear conjugate gradients. And the same thing is also true with LBFGS. And these old nonlinear conjugate gradient solvers and LBFGS just kick the tar out of our algorithms. They're sort of order of magnitude faster, ballpark. Maybe twice as fast, 3 times as fast in general. Okay, so I'm plotting the number of steps on the horizontal axis to find a point where my gradient is less than 10 to the minus 4 across a whole collection of random problems. And basically, LBFGS and these nonlinear conjugate gradients take, 400 steps, and they've solved 100% of the problems. And our methods are taking 800 or more. All right, so we did all this beautiful theory. We proved these optimality results. We said, okay, now we know the optimal method for solving non-convex problems. And then we downloaded some code, and our methods were not as good as everybody else's. Well, we were still better than gradient descent, but much worse than, things we've been using since 1980 or 70 or whatever. Okay. So what now? I think this is the point where you say, well, good thing I do math and I'm a theoretician or something, and you just write a conclusion and call it a day. But I think, what's missing now? So personally, I love the theory. I think it's a beautiful theory. The minimax complexity is really awesome, and it's fun to prove these results. It's very nice. But I think we really, as a field, really need to be thinking about more refined notions of optimality within optimization. This is really, I think, an essential part of where we're going to be going. And what does that mean? I think that it could mean a few things. One is what you might call a more instance-specific theory. I'm not given an arbitrary worst-case function. I'm given a particular function to optimize. And the question is, how hard is the function I am minimizing? All right. And I think trying to understand this question, I think is maybe potentially extremely valuable. And there are some nice approaches in statistics which might somehow point some of the way forward here. There are these ideas in statistics that are called techniques like local asymptotic normality. If you're a statistician, you may have seen some of these ideas. Where here, essentially, the idea is I look at, so if I think about what this is, basically I have my initial function, and I add some kind of I basically randomly perturb it to sort of f of whatever dot minus x0, where x0 is some sort of starting point distributed as normal, 0, and sigma squared over k, say identity, where k is the number of iterations I expect my methods to take. So basically, I add some kind of small perturbation to my function and ask how hard is this to optimize on average. So there are some techniques within statistics that sort of look at basically local perturbations of your function and ask how hard is it to sort of do inference here. And they don't apply in optimization, but essentially translated optimization, this is what they would be looking at. And I think there's some potential here for making forward progress. I'm happy to talk about it more offline or via email or whatever with any of you. Second question is basically better algorithmic development. Can we adapt to different sort of structures, quote unquote, in our optimization problems? They're not going to be worst case. They're going to have some structures within them. What sort of building blocks and structures are there within optimization for us to actually use? Because we're not just solving arbitrary non-convex problems, we're solving structured non-convex problems. And there are going to be sort of structures we can leverage. And so I think going forward, I just want us as a field, and my group is certainly trying to look at questions like this, and I would love it if other folks would as well. I would really like us to start asking questions like this or this and trying to dig into it a bit more. Okay. So that's it for part one of the talk, sort of the theoretical results. I'll take a little pause here and ask if there are any questions.
Adam has a question.
Yeah.
Or just maybe a comment just for some discussion. I think it's interesting that you're bringing this up, these different notions of optimality, and trying to make some sense of more practical algorithms. Yeah, sounds interesting.
Thank you.
Yeah, I'd like to add also to that. I think nonlinear conjugate gradient methods have not gotten enough love in the past 5 to 10 years.
They really have not. Yeah, they have not gotten enough love, and they're really good. They're like disturbingly awesome, and they definitely need some more love. I agree with that.
Yeah. I mean, you could answer that much better than me, but how's the scalability of like a vanilla conjugate gradient method? I don't know.
They're very good. I mean, it really, of course, it certainly depends on the problems that you're looking at, but they are very good. I mean, if you have a problem where you can actually evaluate, the finite sums or evaluate the objective and the gradient, the nonlinear conjugate gradients is essentially as fast as any of these accelerated gradient or other first order methods. It's very fast. So iteration speed is extraordinary. The number of iterations is the time to take an iteration is no more than a typical gradient method. I mean, there are other sort of more sophisticated structures that one can look at, things like where we might use something like Levenberg-Marquardt or Gauss-Newton type methods, when you have sort of certain compositional structures. Courtney is an expert in this, so, ask her. But something like phase retrieval or something like this. So here in phase retrieval, you might have an objective that looks like something like this: AX magnitude squared minus, say, BI absolute value. And here you want to minimize this over, say, C of X in the complex numbers to the n, right? So this is, of course, a wildly non-convex function, but it is very structured. I mean, it's an absolute value, so that's a convex function of some kind of quadratic. There's a lot of structure here. And I mean, it turns out actually this problem, you can totally leverage the structure and do super awesome things. And Courtney has a beautiful paper showing essentially that a subgradient method with Polyak step sizes converges linearly on this problem. Let's see if she's paying attention. Is that accurate, Courtney?
That is correct. That is correct.
Yeah,
And also, I've been interested in the first part of your question, an instance-specific theory, sort of how hard functions.
Yeah, I mean, I think statistical approaches here are going to be essential. And I think the first place we should look at this is in stochastic optimization problems, which is something that we've been sort of doing a little bit because it's easier to use sort of statistical tools to prove bounds here. But in any case, I mean, I think I would love to see work on this. And of course, I would love to solve it. But if somebody else solves it, I would also be like, well, just pumped. So anyway.
I mean, Fabian and I have been working on this in some ways. We haven't taken the approach of kind of the smoothed analysis, which is kind of what you're suggesting, I think, with that instance specific.
It's a little bit like smooth analysis. Yeah, it's sort of like give small random perturbations of your function and ask how hard things are around this function and use that as sort of a proxy.
Yeah, we've just been doing sort of like a pure statistics, just random matrix type approach to solving this type of thing. But we've been interested in it too. So I'm glad other people are.
Well, anyway, so you guys are lucky because you have an expert or if she's not an expert yet, she's soon to be an expert on this stuff. So
Courtney, this was for average case analysis, correct?
What's that, Simon?
The work you're referring to, Courtney, like with random matrix, is for average case analysis rather than worst case?
Yeah, it's like average case. Yeah. So it's like that halting time paper we were working on.
All right, I'm gonna continue on, and I'm gonna dive a little bit into experimental results because in machine learning, which is one of the subfields I work in, we sometimes do experiments, and here now I'm gonna really go. I'm gonna switch into a more polemic mode because I can. All right, so there's this beautiful paper from 1964 by John Platt, Not the John Platt in machine learning, some other John Platt. I don't know. And basically he says, essentially what this paper says literally is follow the scientific method, you ding dongs, but sort of more eloquently. And basically he says, look, strong inference consists of applying the following steps to every single problem in science. And this includes computer science and machine learning, although they didn't really exist in 1964. Formally, explicitly, regularly. Devise a hypothesis, like a strong hypothesis for something. Devise an experiment with multiple possible outcomes, which will actually exclude these hypotheses, sort of prove you wrong. So when you do an experiment, you should have, this is the result I expect. I could be wrong. My experiment could actually falsify my theory or falsify my expectations. And if your experiment cannot do that, then you're just, basically, he says, you're a charlatan. And then you carry out the experiments to get a clean result. Okay, so I actually think this is a really useful view to have. You guys probably laugh at me, you're like, John, everyone knows the scientific method. But let me show you some plots from some papers that I've seen recently. Maybe not so recently, okay. Oh, here's a quote. I actually got this in an email within the last X years. Our experiments conclusively demonstrate that our method A is better than method B. That's not actually possible, right? That's logically invalid. You cannot say that. Your experiments can conclusively demonstrate that you found a problem setting and a set of parameters for your methods and the other methods where your method was better than the other method. That's all you can claim, ever. Anyway, but let's, showing training curves and related plots of information only shows you that basically authors of a paper found a problem on which their method works, and they found a hyperparameter setting for which other methods fail to work. Okay, that's basically what training curves in much of modern machine learning papers show these days. So let me give you a few examples just so you can see them, okay? So here's something that I found. So on this axis is an optimality gap. So these are called training curves. If you haven't seen them, you plot operations or iterations on the horizontal axis, you plot optimality gap on the vertical axis, and then you show some curves where different methods go down or don't go down or whatever. And so in this plot, I guess, this is Sparsa, which is a method by Steve Wright. These are these forward-backward splitting algorithms. This is a projected gradient method. This is an interior point method. And here's a quote from this paper. The stochastic, here's another training plot where we have some stochastic gradient type methods, forward-backward splitting, projections, and some non-stochastic methods. I'm reading. The stochastic methods, Phobos and projected gradient, were significantly faster than any of the other methods. This is by these two guys, I guess, I don't know. They're still involved in machine learning somehow. But like, this is ridiculous. I mean, whoever these authors are, they found a problem where their method was better, and then they claimed that their method was better everywhere, right? I wonder if I have more examples like this. Oh yeah, I totally have more examples like this. Look at this. Okay, so for the second experiment, we fit this neural network model. We show a substantial performance gap between gradient descent and the other methods. And so we're plotting again, number of steps and function value over time, and like kind of averaged over a bunch of experiments. But basically, this is not particularly informative. It shows you that there's a problem where certain methods do better than others. Right, and I don't think we should be presenting results like this in optimization or in machine learning or anything like that, okay? And obviously I will be the first to admit that I do this because all of these plots were from my own papers in the last several years, okay? So anyway, so I'm sorry for the extent to which I've perpetuated this crime against science. I am as guilty as anybody, but I think we need to stop. All right, so how can we stop doing this? Or what are some ways we might do this? So I think we should think about presenting results in a few different ways. And some of these ideas are, these ideas are out there. Just I want to highlight them and argue that we should be doing it and sort of talk about how we might do it. So one is I think we should start really thinking carefully about sensitivity analyses. You come up with some method. How sensitive is your method to hyperparameters and other changes? Right. And another idea might be to go back to performance plots. And these are I don't want to say old, but not super recent, by Dolan and Moret from 2002. Basically, you kind of come up with a collection of challenge problems, and then you basically run a bunch of methods on all of your different problems and then sort of rank them. How often are they, in the top 1 or 2 or 3 of the best performing methods? And these are the kinds of things I think we should be thinking about as we present empirical results. And even, frankly, I think it might be plausible to give theoretical versions of these results too, but that's a different question, okay? So let's let me just give one example of this in some papers that we've done, trying to get at some of these ideas and understand them. And in particular, sorry, I'm going to focus on the sensitivity analysis. You know, how sensitive is your method to parameter and other changes? So to do this, I need to set up a little tiny bit of notation. So just ask, how do we solve optimization problems? Well, we solve an optimization problem by, you know, if I want to minimize a function f, I build a good but sort of simple model of my function f, and then I minimize the model maybe with some regularization. So what does that mean? Well, gradient descent says I'm going to make my model. And by the way, I'm going to always write my model is centered around x, centered at x, and then this is the argument to my approximation function or model function to my model. And so what gradient descent does is it says around my point x, I'm just going to do a first order expansion of my objective. So in this picture, right there is my point x, and then this is my model. So let's draw that in red. My model is this red dotted line, y maps to fx of y, which is the first order model. Newton's method, of course, makes a second order model. So around the point x, again, we have a quadratic model. So this is fx of y as a function of y. So y going this way. Right. You can imagine all sorts of other models of functions. Let's take a quick look at this in the context of stochastic optimization. So, you know, we can think of most optimization models or optimization methods as basically iterating and make an approximation to a function centered around some current iterate xk, make this approximation, and then I minimize it plus some kind of penalty for moving far or some regularization. We're going to think about this in the context of stochastic optimization. So here, S is some random sample from an underlying population, and I want to minimize an expected loss or an expected function value. So how are we going to iterate? Oh, I'm sorry, what are our models going to be? Well, let's just think of what we're going to have as a, excuse me, our models are always going to be convex functions. Our models will be lower bounds on the true function value and correct at our current iterate, or at least at the point where we center our model. And then sometimes I'll assume that they have an accurate lower bound. So how should you think of this? Basically, you should think of this one as if you're solving a machine learning problem, you have a loss function. When you have a loss of 0, you're perfect. Thanks, Tim. And if your model or approximation of your function says your losses are less than 0, but you know that 0 is the minimum, maybe just stop at 0, because negative numbers are poor approximations to positive numbers. Right? That's the deep insight. So stop at 0. So just a quick picture. You know, if this is my point x, so x0 is where I'm going to center my model. That's x0. First order model is just that line. This sort of what you might call a truncated model, just says, hey, I'm using something like the squared error, or I know my losses are non-negative, I'll stop at 0. We can imagine a bunch of different models like this. You could also just not even make an approximation. So anyway, so let's think about these iterations and ask, okay, so what's going to happen when we iterate? We're going to minimize we're going to draw a random sample from our underlying population, and then take some kind of stochastic update step with one of these models, either the truncated model or the linear model or something else. Okay, so I'm going to consider 3 things: stochastic gradient, this truncated gradient, which just says stop at 0, don't cross zeros, and then I'll use a what you might call a stochastic proximal point method, where we're not making any approximations at all to our random functions. So we're going to iterate this guy right here with one of these 3 models. All right. So here are some plots. These are what you might call sensitivity analyses. So in each of these, what I'm going to think about is this step size choice. So this is sort of the analog of the step size in a stochastic gradient method. And we're going to vary this. We're going to set alpha k equals to some initial alpha 0 multiplier times 1 on, say, square root k. And then all I'm going to think about is what happens as I vary this parameter. Okay, so that's what I'm going to show you guys in these plots, just to try to understand, hey, does it matter, these methods? Okay, and the answer is yeah, it matters a lot. I mean, this is not surprising to many of us who've ever run a method. But basically, you run, say, the stochastic gradient method, you look at this initial step size, and it works very well for solving a linear regression problem with low noise in a regime from, say, 10 to the minus 1 to 2. But then outside of that region, the stochastic gradient method oscillates wildly. Similarly, but now when you use these sort of more sophisticated methods like proximal point or truncated methods, this is the don't cross zero method, you get a much broader range of step sizes where these methods are effective. Okay, much, much broader. You can, oh, and just so we're clear, this is the time, the number of iterations it takes to solve a problem to a given accuracy, and this axis is the initial step size. We see the same plot if we have no noise in linear regression. You can do this with linear regression with poor conditioning. So here's a plot. I'm just running, literally, I'm trying to minimize, 1 on 2m, ax minus b, 2 norm squared. But here now my matrix A is supposedly poorly conditioned. So can anybody guess? And so what we're seeing here is that basically the stochastic gradient method didn't converge within 1,000 iterations for any of our possible step sizes. These better model-based methods are actually pretty functional. I mean, they're noisy, but they're doing pretty well. They're actually converging for a broad range of step sizes. So can anybody guess what the condition number of this matrix is? I'd say it's poor. It's 15. Yeah, that's not actually very big. That's pretty small, right? And the stochastic gradient method, which evidently is the workhorse for all of machine learning, is just non-functional here. So phase retrieval, the same plot happens. Anyway, okay, that's a performance plot. I don't want to dwell too much on that. It's a beautiful idea. I want to finish up here because I don't want to take your guys' time too long. Let me just conclude and say, listen, I think thinking about plots like these and other versions of sensitivity where we really try to evaluate, hey, when is my method functional and when is it not? How sensitive am I to, say, step size choices or other problem type parameters, conditioning, things like that? How sensitive am I to that? I think it's a useful thing to think about. And I think, for one, I think we need to be as a community honest about whether convergence rate is an intellectual contribution, hey, I'm minimax optimal, or it's real. Like, yeah, this convergence rate matters and I'm actually achieving like better results on meaningful problems. I think it'll be really useful if we can, as a community, also build test sets or challenge data sets with a breadth of problems that actually allow us meaningful evaluations of optimization methods at scale. And there are, and I'm sorry, there's a citation I'm missing here, and I'm blanking on the name, but there's a fellow in Germany who's actually working on this and doing some really cool ideas there. And I can find the citation if somebody asks. Another thing, we should have testable hypotheses. You should be able to be super wrong. When you say, okay, I proved some stuff, according to my theory, these are the results I expect to see, you should be able to fail. Your test should be able to fail and you can be wrong. And I also think that just it'll be fun, and I'm glad to hear that some of you are working on these kind of questions, but let's build a better theory of optimality beyond this kind of minimax worst case sense. Let's demand adaptivity. Let's demand robustness to problem choice. Let's demand robustness to method parameters and things like that. I think we really should be thinking about these ideas as a field. And it's not to say we're completely or not, but I just think there are some beautiful opportunities here. And I would love it if we could all, maybe not all, but if we could be pushing in these directions. So anyway, so thanks a lot for your attention. Really appreciate all of your attendance, and I'm happy to take more questions. Or I guess I could like use my honorarium to buy everybody a beer. Is that a thing I can do? I don't know how that works.
There's no beer emoji.
There's no beer what?
Emoji. There's only.
Oh, there's no beer emoji. Yeah. I guess I could do that. I could get the honorarium, and then you guys can all send me your Venmo, and I can then buy all of you a beer, because there's only like 20 people here.
Oh, there were at some point 44, 45 people.
That's good. I scared them all away.
No, people had to leave, unfortunately. But I'm sure. First of all, let's thank the speaker again. That was a very, very nice talk. I think from all of us actually, or for almost all of us. I'm sure high level and still very informative. And so I assume there might be some questions from the audience.
I'd love to take them.
Please feel free to unmute yourselves.
Just shout them out. Although I appreciated the interaction in the middle of the talk. So you guys, it's nice to give a talk and feel like people are paying attention because there are questions happening. So thank you to all of you for indulging me in that. I really did appreciate it.
I can ask a question.
Yeah. Good.
So how sensitive are your sensitivity plot to epsilon and this kind of thing?
Oh gosh.
Over K.
Great question. Let's see. So I said, okay, so I said, what we're going to do is measure sensitivity to initial step size multiplier, and I'm going to use a fixed step size sequence of 1 on root k. Okay, so alternatives could be, instead of 1 on root k, we could instead use 1 on k to some power beta, where beta is between 0 and 1 or something like that, or different things like that. The plots are not really sensitive to this. So we have done kind of additional experiments where we basically look at a 3D surface where we're varying both that step size rate and the step size multiplier, and you do see similar things to these kinds of plots where there's a narrow valley where stochastic gradient methods will work, and these more sophisticated model-based strategies have a much broader sort of like plateau or valley or something where they're functional. Now your second question was, okay, what epsilons did I choose? Like, I'm plotting the time to epsilon accuracy. Well, how do the plots change? Does I change epsilon? And I don't actually remember. I'm sorry. And I'm not actually going to speculate. It's my recollection is that it kind of depended on the problem. Like for phase retrieval, for this problem, and not sensitive to epsilon at all. I know that. Like, you could change epsilon and these plots looked all completely the same. I mean, certainly like the times would go up if you picked a smaller epsilon and go down if you picked a lesser epsilon, but it was sort of the same qualitative picture. So for this one, I'm very confident it stays the same. For this one, I'm less confident. So I don't 100% know. And that's a good question. I should know the answer to that, but I don't.
I would like to also ask or actually comment also on this sensitivity idea. I think there's actually a good opportunity maybe to link this to traditional like sensitivity analysis and all these powerful tools that variational analysis has kind of brought to the table. I mean, for example, that your first example is essentially kind of a question: how sensitive is a proximal operator with respect to the proximal parameter as opposed to the base point? I mean, it's not the full answer, but these kinds of questions are in there. And I think that there could already be some good tools to analyze these kinds of questions. I'm not saying we'll answer everything, but I mean, there's powerful things already in the literature, I think.
Yeah, there certainly are. And I should also, like, certainly this is not an exhaustive survey of all the different methods out there. I mean, as you guys know, Simon has done some very good work on kind of like accelerated gradient type methods, which are related somehow to proximal point methods. And there are methods like catalyst and stuff like this, which I am not really touching. So there are a lot more methods out there, and many of them do show different flavors of robustness. But we haven't totally done sufficient experiments with all of these. But yeah, so I would say these results, even as they are perhaps a little bit partial, but they kind of get at the idea that, yeah, let's try to understand sensitivity and things like that here.
Okay, there are more exclusively positive comments in the chat.
It's because everyone's nice and Canadian.
More questions or comments from the crowd?
Hi. Fabian, you raised your hand, right?
Fabian raised his hand. He's just waiting.
Oh, okay. I was saying hi, but since I have the floor, so you mentioned some criticisms to Minimax analysis at the beginning. Would you care to speculate what would a theory that would satisfy you look like? Like, for example, if you had to give something up to get a better theory. So for example, you had to restrict yourself to quadratics, or you would have to assume more smoothness, or you'd have to put more structure on your objectives.
Yeah, great question. Like, how do you move? What are the different ways beyond?
Yeah.
So I think I'll highlight, say, like 2 or 3 different ideas One idea is what you might call like, is basically moving to stochastic optimization and using kind of local minimax ideas. Because essentially the idea here is that essentially I take my function f, I randomly perturb kind of the point around which it's centered, which of course just shifts the optimum, but I don't actually observe f, I observe noisy gradients from f. And then you can basically use statistical tools to say that, hey, in some sense, this is kind of like observing just perturbed observations from a Gaussian mean or something like that. And then you can say sophisticated stuff there. Okay, I mean, we haven't completely nailed all of that down, but it's plausible. And I think that that's an avenue that my students and I are kind of looking at. And I think we may have some success there. Okay, so that's one. But I think there are other variants of this that are going to potentially be really interesting. Another, and this is something I'm really curious about, is what you might call oracle complexities. And I don't mean this in the sort of standard convex optimization oracle. I mean, basically I come up with a method and it has some performance. Then I can ask, okay, now here's another family of methods, say gradient methods, okay? And if I can prove, say that, my method beats every method in, among some alternative class, say like gradient methods with a fixed step size or something. Say, my method is of course using more information, but because it can be adaptive to step sizes, it will always have a better convergence than any, fixed step size gradient method. Or it will do as well as though like you chose a step size optimally in your gradient method or something like this. Sort of like picking comparator classes that are slightly weaker than the methods that you're running and then saying, hey, I uniformly dominate them. And then you sort of feel like, oh, that's a cool thing. I mean, we see this in statistics a bunch, where like if you've seen like the lasso or something like that, you prove things like, hey, if I run L1 regularized linear regression, it does almost as well as if I told you ahead of time, here are the zeros in my solution vector or something. So I think some idea along these lines would be very cool. Or say like, I'm going to run, Saga or some kind of accelerated stochastic procedure. And I guarantee, and I use more information because I have to keep memory around if I'm running Saga, right? Simon, is that right? I have to remember some things.
Yes, you do. But you can do SVRG and then you don't need.
Yeah, but anyway, so I do some slightly more sophisticated thing. But maybe we could prove that this is sort of like uniformly dominates very naive, like fixed step size stochastic gradient methods or something in some sense. I mean, that sounds hard to do, but it's totally believable, for one. And two, then you feel like, okay, this is not like a pure optimality result, but it really tells you like, hey, I do as well as, these other methods that we sort of accept as being okay, but I actually am dominating them. So it's sort of a different way of viewing complexity. So I think that's another
setting. You would restrict a lot the class of problems that you're looking at.
Potentially, yeah. Yeah, maybe, I mean, even if you just prove this for, say, quadratics, you're like, yep, I dominate on quadratics. Already you sort of feel like, hey, I think I would see that and be like, hey, that's a nice approach. That's a really cool insight. Mm-hmm. Of course, it doesn't answer every question, but it's sort of it's a different way of looking at optimality, and I'd love to see that. So I think that's plausible. I feel like I'm giving you guys all my secrets, but I don't care. I just want to see. I want the answers to these. So here's my next grant application.
Well, you're giving it to everyone because I think it's recorded.
Oh, good. Yeah. But that's fine. I think it'd be super cool to see this stuff, and I would love to. I think it'd be really awesome.
Thanks.
Okay, I think there was one more hand raised in the chat or in the participants window. Danny Wu.
Oh, hi. So just out of curiosity, for these methods that establish lower bound for stochastic optimization, do you think it's also possible to establish a similar lower bound for sampling problems? Say like I'm trying to sample from a distribution whose potential is defined by like x of minus fx, and f can be convex.
Ooh, I actually haven't really thought about that.
Because I'm not aware of any kind of like lower bound for like sampling algorithm like Langevin Monte Carlo, things like that.
Yeah, good question. I would guess some of the tools. I guess if I were to look into that, I think I would first start with sort of the. If I were to look into something like that, I think I would first start with some of these tools in stochastic optimization, like this paper here, which provides sort of an information theoretic view on optimal complexity within optimization. I think these tools may be more useful, maybe a useful starting point there. I guess that's where I would start and try to build off of. But yeah, I also haven't seen it.
Thank you.
Hi.
Yeah.
So when you say adaptivity to structure, do you know about this recent line of work that tries to consider functions that might be locally smooth or only locally Lipschitz? And are you referring to that sort of structure where you might have, so in optimization, we usually assume this function is globally smooth or globally Lipschitz, but this may only be satisfied locally. And there is this recent string of papers that is pretty nice on the topic.
I may know the papers,
okay.
which particular,
okay,
which authors?
Okay, so there is a recent work by Suvitra, I think, and some co-authors from MIT. It was about optimizing non-smooth, non-convex functions. I think it will be in Neurons or ICML. And yeah, the main point that they had was that they only assumed that f is directionally differentiable, and that it is Lipschitz only locally, so on closed convex sets. And they basically proved that you can always adapt to this sort of local Lipschitz constant. You don't have to suffer with the global.
Yeah. I'm not. I guess okay. I have two answers to this. One, I haven't seen this paper, so I guess no is a partial answer to that. There's also, so Frank Curtis and gosh, I don't remember who the co-authors were, looked at some questions of exploiting certain local structures within general optimization, and that's in mathematical programming. But I guess this is more just sort of no, there was nothing in particular I had in mind here. Just I guess I just want to just understand different things. I mean, as the sort of simplest example that I always come back to is these compositional problems. So this is again inspired by Courtney. So I say, I have a function, f of x is the composition of a convex function, and C is, say, like smooth.
Yeah.
Because then, of course, I can make a very good model of this by just linearizing only C, right? Plus grad C of x transpose y minus x, right? So now this is convex in y, and it's locally very accurate. So this is sort of a structure I could exploit maybe somehow. And this is the kind of structure you see in these phase retrieval problems, matrix completion, things like this. But yeah, I don't know that I had sort of deep thoughts in this direction. I think, but I do like the idea of saying, here are like structural building blocks that we can leverage to say interesting things. I mean, I guess another structure which Simon has been, which is now a little bit older, but Simon has been a big part of investigating here, is like finite sum structures. 1 on M, sum I equals 1 to M, fi of x. That's another structure that's sort of a nice building block off of which you can leverage things. But again, these are, I don't know, it's just sort of a, I don't know, view of how to, maybe we should be thinking more carefully in this direction, but I don't have any, I'm much less concrete on this one than the next steps here, I think. Simon, you have your hand up?
Thank you.
Yeah, good question though.
Sure, yeah, if we still have time for questions. So I was just curious to know your take on pre-registering experiments. So this is something we've been discussing recently at MILA, and given that you're talking about like making hypothesis and doing the scientific method. So what about pre-registering optimization experiments? Have you seen this? What's your opinion?
I have not seen it. I guess the answer is that it depends. I mean, if we have like I can imagine two worlds. One is where we have sort of a fixed collection of challenge data sets, which is sort of what we live in right now. There's ImageNet, there's well, CFAR and some others, and you know, and then some big NLP type data sets and things like this. So if we have a fixed collection of challenge data sets, then I think pre-registration is probably really important. And I think it'd be really, I don't know, it's sort of, I don't exactly know how you would enforce it. Also because for some of these things, the experiments are so big that like the only people who can do it have massive computing resources for some of these large scale problems. Now, on the other hand, you could imagine you have like a test data set generator somehow, which sort of generates random problems on the fly, which somehow we've convinced ourselves are a good proxy for a wide range of problems. And for those, it's sort of, I feel less like you'd have to pre-register. I mean, sure, you could still overfit to that even if it wasn't sort of diverse enough. But I don't think we have that yet. But yeah, I don't know. Did you guys have thoughts of how you could actually get people to pre-register things and evaluate whether they'd actually follow through with that? No. Yeah, I should probably think more carefully about that. Yeah, is the answer.
Okay, I think it's a good time to end the official part and stop the recording at least.